on. Do it. Do it.
Do it.
Do it.
Do it.
Do it. Do it.
Who is doing it?
Do it.
Do it.
All of it.
Do it.
Come on. Do it now.
And I will do the rest.
Testing 1, 2.
Take me higher. I'm reaching out across the sky, chasing shadows, learning how to fly. Every heartbeat pulls me closer now to a place where we can touch the clouds. Feel the light within.
So, I would like to go over. Okay, I got some audio here. So I'd like to go over. First of all, I want to say I got a comment in the last video we did about MOSFETs and how they handle the backspike from Society of High Sciences. And I would like to go over the MOSFET. I found a nice video here from the links in the chat from Mr. Foolish Engineer. I'll post this channel link as well. So, let me make sure the audio is good. Testing 1, 2. All right, we're good. So let me share the screen here.
Through the echoes of light, my friend, take me higher now.
All right, here he's showing you a N-channel MOSFET. Okay. So basically, here's the flyback voltage. Let me just take a screenshot of that. Yeah, good video. Well, anyway, I kind of learned this in school like 25 years ago. And can you blame me for forgetting? Anyway, I forgot most of the stuff I learned in school. ITT, Technical Institute. It's in there somewhere, just I don't use any of it, you know. Not until I started, experimenting, about 10 years ago. Yeah, so what is he showing here? Yeah, so he's explaining how you can put a diode on the coil and send it back to the battery. Testing 1, 2. So, yeah, it looks like you can, based on what I'm seeing here, this makes my double pole circuit obsolete. You don't even need a double pole switch. You could just put one flyback diode across the inductor. Which is the case. Wow, well that's awesome. And it sucks at the same time because I worked so hard at that double pole. It's live and learn, It's a good experience either way. Yeah, so that's what it looks like. And still though, I'm a little bit skeptical on how much of that positive flyback will go to the battery when that coil is in line with it. Because, that the coil will take some of that positive flyback on the other end. And it will turn it into a magnetic field and get wasted if you don't use it. So sending it back to the battery without the coil in line it kind of makes sure that it gets stored instead of sent back to the coil. Either way, it's good to know this stuff. So let's bring up the screenshot. So this is Foolish Engineer, and he's explaining how a MOSFET works and handles the flyback. So I still don't see how the MOSFET itself is doing it here, because I see him drawing a diode returning the line. So. Alright, the gate is the voltage applied to the coil. Spike happens. Alright, let's play the video and listen to it.
It goes beyond the safe operating area of the drain to source voltage limitation of the MOSFET. And this MOSFET will damage, which will short all the MOSFET terminals within a small period of time. We have discussed the safe operating area of the MOSFET in a previous video. Please click here to watch that video. Well, this happens because the inductor opposes change in current. Whenever the MOSFET is turned on or turned off, there is a change in the flow of current in the circuit. The inductor stores the electromagnetic energy inside of it. So when the MOSFET is turned on, the current will flow to the inductor. And when we turn off the MOSFET, the current stops flowing to the circuit. This inductor doesn't like that, and it forces the flow of current through the circuit in the same direction. Hence, due to change in current with respect to the time and the inductance of the inductor, it induces some voltage at this point, which is known as the flyback voltage of the inductor. So when the MOSFET turns off, this flyback voltage and the supply voltage adds up at this point, and we get the huge spike across the MOSFET. After some point, this drain to source voltage comes back to the supply voltage. Well, to minimize this, we need to find a way where the energy stored in the inductor should dissipate or be sent back to the supply. The easiest way to do that is to put a diode in parallel with the inductor, and it solves our problem very easily in a cost-effective way. When a MOSFET turns off, the current flows to this diode because the flyback voltage acts as a voltage source. Diode goes into forward bias and current flows to the diode, which discharges this inductor, and energy goes back to the supply voltage. This diode has many names such as flyback diode, anti-parallel diode, reverse bias diode, or freewheeling diode. Because this diode is acting like a freewheel which goes with the flow of this current. Well, we understood why we need a diode for an inductive load to control it. But when we use this diode, it adds some limitation in our circuit as well. Let's say now the MOSFET is turned off. If we need to turn on the MOSFET again, this diode exhibits some strange characteristics. When the MOSFET was turned off, this diode was forward biased and current was flowing to the diode. When the MOSFET is turned on, the current will flow from the supply through the inductor, so the diode will be reverse biased. When a diode is switched from forward to reverse bias, a reverse current flows for a short period of time through the diode due to its intrinsic property. And the time period for which this current flows is known as the reverse recovery time of the diode. If we see the graph of the forward current of the diode, initially it is in positive x-axis region when the MOSFET is turned off. Now when the MOSFET is on and the diode is off, still a small amount of current flows in a negative direction, which comes back to normal stage after some time. And if we see the waveform of this diode in a DSO, it looks like this. And this is the reverse recovery time. This current adds up for a short period of time to the inductor current when the MOSFET turns on. So total drain current increases for a short period of time in the MOSFET. This reverse recovery time and current plays a very important role in the MOSFET switching, which we'll see in the next video, where we will understand how a MOSFET behaves when there is an inductive load with waveforms. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to
Flyback converter works in two main phases. First, energy storage phase, and second, energy transfer phase. In energy storage mode, when the MOSFET is turned on by the controller IC, current flows through the primary winding of the transformer. The transformer's primary winding stores energy in the form of magnetic field. During this phase, the secondary side of the transformer is disconnected because the rectifying diode is reverse biased. Hence, no energy flows to the load. The energy here acts like a bucket being filled with water. The energy is temporarily stored and will be transferred during the next phase. In the next phase, which is energy transfer, when the MOSFET is turned off, the magnetic field in the transformer collapses. This collapsing field induces a voltage in the secondary winding of the transformer. The rectifying diode on the secondary side becomes forward biased, which allows energy to flow into the output capacitor and to the
Well, that's another way you can capture the flyback without a double pole switch. Only thing is, I'm not seeing how the MOSFET.
Last time we saw which parameters we should check while selecting a MOSFET. This time we'll see how a MOSFET switching works and what all things are important for it. So let's start. We'll check the dynamic characteristics of the MOSFET right now. These parameters are very dependent on the condition that determine how we measure them. These are very helpful for switching applications and have a very crucial role which determine how fast a MOSFET can switch on and switch off. If we check a MOSFET, there are some parasitic capacitance and resistance present inside. If we see this simplified equivalent circuit of an N-channel MOSFET, we can see there are capacitance between gate to source, gate to drain, and drain to source, and resistance at drain, gate, and source. The gate to drain capacitance is also called as the mirror capacitance. This mirror capacitance is very important for switching characteristics because the CGS and CDS stay constant in the switching cycle, but the mirror capacitance changes. Well, we know when we provide VGS, the MOSFET turns on and VDS decreases across the MOSFET and current starts flowing through it. Now, this mirror capacitance is low when the MOSFET is turned off. But when the MOSFET is turned on, the VGS increases and VDS starts decreasing. There is a point where VDS becomes equal to the VGS, and at this point, reverse transfer capacitance and output capacitance. The input capacitance is tentatively equal to the mirror capacitance. We provide a gate to source voltage at the MOSFET. Charging through the internal MOSFET switches off. And fall time is measured when the MOSFET is turning. Hey, welcome back once again. This time we'll see how a MOSFET behaves when there is an inductive load with its gate to source voltage, drain to source voltage and drain current waveforms. So let's start. I recommend you to watch that video first. If you have already watched that video, please skip to this timestamp. Freewheeling diode. And what is the reverse recovery of this diode? Equal to the mirror capacitance, freewheeling diode, and what is the reverse circuit due to inductor switching. In that, we saw why do we need a freewheeling diode and what is the reverse recovery of this diode. Please watch it by clicking on this card above. Now let's take this circuit. MOSFET is switching this inductive load and it's being used as a low side switch. We'll see the gate to source voltage, drain to source voltage and drain current waveforms of the MOSFET while it is turning on and turning off. We'll divide this operation in multiple time periods. Before we start, we are considering that the inductor was discharged to this diode at the previous turn-off process of the MOSFET. So while turning it on, this diode will exhibit reverse recovery characteristics in the circuit. At time t0, we give a gate to source voltage to the MOSFET, which increases gradually, and it charges the input capacitor of the MOSFET with internal resistance of the driver circuit. At time t1, the gate to source voltage of the MOSFET reaches to the threshold voltage, causing current to start flowing in the drain. In period t1 to t2, the drain current increases in proportion to the gate to source voltage, but drain to source voltage stays constant due to this diode. At time t2, the MOSFET carries the entire load current. In this, the reverse recovery current of the diode is also added, so the drain current increases further. At time t3, the drain current reaches the maximum value. Up to this point, the drain to source Hey guys, we all know engineers use 12-volt battery in our vehicle and all the circuits present in the vehicle work on this 12-volt battery and alternator of the vehicle. But if anything goes wrong with these systems due to any small reason, then it would be a disaster. Our vehicle won't turn on at all. So we need to protect 12-volt automotive systems. In this video, we will see one of the most famous protections that we need to use, which is known as reverse polarity protection. So let's start. Let's say during maintenance, where the battery positive and negative leads may be connected in the opposite polarity. Due to that, the internal circuit of the system might damage. Or there will be a short circuit between battery positive and negative terminals. To avoid that, we use reverse polarity protection. There are 4 methods through which we can do so: PN junction diode, Schottky diode, N-channel MOSFET, and P-channel MOSFET. We use these components in series with the circuit, so the whole circuit current flows through these components. Well, the main loss in the application is due to the conduction only. Now we can segregate which component to use for our application. First is the PN junction diode. Using a rectifier diode as a blocking diode is the simplest and most cost-effective way to apply a reverse polarity protection circuit. When we connect recovery rectifier in series with the load, it ensures that the current would flow through the circuit only when the battery is correctly connected. When the supply pin is connected to the battery positive and negative is connected to the ground, the circuit will work fine. But when the connections are reversed, the diode would get reverse biased and it will block the current flow, acting as an open switch and shut down the system. Well, there is no need for control input for this circuit, which gives us low complexity and low component count. However, using this rectifier diode comes with a high forward voltage drop of the PN junction. This is the reason why these diodes are only used for low power application for load currents below 1 ampere. Also, we should consider inrush current through this rectifier. For example, when the battery is connected to the circuit, the bulk capacitor present in the system begins to charge very quickly, which gives rise to inrush current. We should check the peak current and duration of the pulse to ensure it does not exceed the specification mentioned in the datasheet. We can calculate the conduction loss of this diode by using forward voltage drop of the diode given for a steady state temperature of the PN junction and the load current. For example, if the circuit current is 0.8 amperes and VF of the diode is 1 volts, then the conduction loss would be around 0.8 watts. Nevertheless, the maximum total power dissipation of the rectifier diode has to be below the maximum limit given in the datasheet. If you use this diode for high power applications, then the losses across this diode would be huge, which will decrease the efficiency of the circuit, increase the temperature of the diode, and eventually it will fail. In order to overcome the high conduction losses of a rectifier diode, we can use a Schottky rectifier diode for reverse polarity protection. A Schottky diode comes with the same advantages as a rectifier diode, that is, there is also the least complexity. Additionally, it has very low power dissipation compared to the PN junction diode, and due to that, it can be used for higher load currents up to approximately 3 amperes. The power loss of this diode can be calculated with the same formula. If the circuit current is 1.5 amperes and VF of the diode is 0.5 volts, then conduction loss of this diode would be only 0.75 watts. Now, when we see the difference between the rectifier diode and Schottky diode, even though the current across the Schottky diode is high, still the conduction loss across it is lesser than the rectifier diode. However, Schottky rectifier comes with a higher leakage current due to its metal semiconductor interface. When the junction temperature of the Schottky diode increases, the leakage current becomes significantly larger, which results in unwanted effects such as thermal runaway. Similarly to the rectifier diode, inrush current through the diode must be considered. The peak current and the duration of the pulse must be checked to ensure it does not exceed specification. Like in the case of recovery rectifier, the conduction losses can be calculated by multiplying the temperature dependent voltage drop with the load current. Also for Schottky diodes, the junction temperature should not exceed the 175 degrees Celsius. Next device for reverse polarity protection is P-channel MOSFET. In this application, the MOSFET works in two different modes. First is diode mode and MOSFET mode. We saw in one of our previous videos, during the manufacturing of the MOSFET, a parasitic PN junction diode is created within the MOSFET cell. We connect a P-channel MOSFET like this in the circuit, where the drain is connected to the supply of the system and source is connected to the load. We connect a pull-down resistor from the gate of the MOSFET to the ground and connect a Zener diode from the source to the ground for protection. The Zener diode will clamp the gate of the MOSFET to its Zener voltage and protect it against overvoltage. When the MOSFET is not energized, that is, the gate terminal does not have a sufficiently negative voltage below its source to exceed its minimum threshold to turn on. And when the battery is connected correctly, it behaves as a forward bias diode. The power loss in the device is product of the forward diode voltage and current flowing through it. Once the gate to source threshold voltage is reached, the MOSFET turns on and switches from diode to MOSFET mode. Current then flows through the drain to source channel, and the power loss is the product of RDS on of the MOSFET and square of the current flowing through this channel. When the reverse polarity is connected, the MOSFET will be switched off because the gate to source voltage for this case will be positive. Conduction loss of this MOSFET would be so less. For example, let's say the RDS on is 0.1 ohms and current is 4 amperes. Then the conduction loss across this MOSFET would be only 1.6 watts. The next possible protection circuit can be constructed by using N-channel MOSFET. The majority of the advantages of P-channel MOSFET also apply to N-channel MOSFET. The major difference between these components is basically to enable an N-channel MOSFET by providing the positive VGS. And the biggest advantage of this N-channel MOSFET is that it is capable of conducting larger currents compared to P-channel MOSFET, as the RDS on of the N-channel MOSFET is much lower than the P-channel device. So there is significantly low power dissipation, and the N-channel device is much better suited for application which require larger currents. We need to add a complicated gate driving circuitry to turn on this N-channel MOSFET, which increases the cost and complexity of the circuit. If we summarize these circuits, we should select the reverse polarity protection circuit based on our current, complexity, and cost requirements for a particular system. Well, that's all about the reverse polarity protection part. I have added all the references related to these circuits in the description. If you have any query, you can ask me in the comment section or email me. Hit the like button and subscribe to my channel. And finally, thank you so much for watching this video.
Well, I didn't see anything about the back spike going through the MOSFET. All I see is that the MOSFET stabilizes the back spike. Let me see here.
Considered. The peak current and the duration of the pulse must be checked to ensure it does not exceed specification. Like in the case of recovery rectifier, the conduction losses can be calculated by multiplying the temperature dependent voltage drop with the load current. Also for Schottky diodes, the junction temperature. The Zener diode will clamp the gate of the MOSFET to its Zener voltage and protect it against overvoltage. When the MOSFET is not energized, that is, the gate turns. Hey, welcome back once again. Last time we saw how a MOSFET is used to control a resistive load. I recommend you to watch that video to understand the basics of MOSFET switching. This time we'll see how a MOSFET behaves when there is an inductive load in the circuit. So let's start. Voltage to the MOSFET so that its input capacitor charges. And to turn off a MOSFET, we remove gate to source voltage from the loads to the second is used as a low side switch to the drain of the MOSFET, which controls the turning on pulses to the drain on. We see a sudden spike in voltage in the second pulse. Voltage spike comes this will these again in the second pulse. We remove the gate to source voltage. We see a sudden voltage spike in the drain to source voltage of the MOSFET, and this voltage comes back to normal supply voltage and MOSFET turns off. We turn on the MOSFET again in the second pulse. We provide the gate to source voltage and drain to source voltage goes to 0. After this, When we turn off the MOSFET, this voltage spike comes back again and goes back to the normal is used to control a resistive load. I recommend you to watch how a MOSFET is used the basic. There is an inductive load in the circuit. We'll see how video to understand the basics of MOSFET switching. This time we'll see how a MOSFET behaves when there is an inductive load in the circuit. So let's start. Those who have two types of enhancement mode MOSFETs, which are categorized as N-channel and P-channel MOSFET. We'll use an N-channel MOSFET to control a load in this video. To turn on an N-channel, we remove gate to capacitor charges. And to turn off a MOSFET, we remove gate to source voltage from the MOSFET and discharge the input capacitor. There are a lot of inductive loads which we use in many of our circuits. The best inductive loads are a motor, relay, videos. This is the basic diagram of a circuit where MOSFET is used as a low side switch and inductive load is connected which controls the turning on pulses to the gate of the MOSFET. When the gate to source threshold voltage is applied, the drain to source voltage goes to zero, current starts flowing to the circuit and MOSFET turns on. But when we remove the gate to source voltage, we see a sudden voltage spike in the drain to source voltage of the MOSFET and this voltage comes back to normal supply voltage and MOSFET turns off. We turn on the MOSFET again in the second pulse. We provide the gate to source voltage and drain to source voltage goes to zero. After this, when we turn off the MOSFET, this voltage spike comes back again and goes back to the normal supply voltage. This behavior keeps repeating at every turn on and turn off cycle. Well, these spikes are present in the waveform for a very short period of time, which are of a very high amplitude, and sometimes it goes beyond the safe operating area of the drain to source voltage limitation of the MOSFET. And this MOSFET will damage, which will short all the MOSFET terminals within a small period of time. We have discussed the safe operating area of the MOSFET in a previous video. Please click here to watch that video. Well, this happens because the inductor opposes change in current. Whenever the MOSFET is turned on or turned off, there is a change in the flow of current in the circuit. The inductor stores the electromagnetic energy inside of it. So when the MOSFET is turned on, the current will flow to the inductor. And when we turn off the MOSFET, the current stops flowing to the circuit. This inductor doesn't like that, and it forces the flow of current through the circuit in the same direction. Hence, due to change in current with respect to the time and the inductance of the inductor, it induces some voltage at this point, which is known as the flyback voltage of the inductor. So when the MOSFET turns off, this flyback voltage and the supply voltage adds up at this point and we get the huge spike across the MOSFET. After some point, this drain to source voltage comes back to the supply voltage. Well, to minimize this, we need to find a way where the energy stored in the inductor should dissipate or be sent back to the supply. The easiest way to do that is to put a diode in parallel with the inductor.
Okay, I was talking to myself, I was muted. So what I was saying is, so basically, yeah. How do I put this to you guys? The MOSFET does not recycle the flyback, okay? It stabilizes it. You know, when you put your plus here from your battery source and your minus there, and then you open this switch and it flies back. What happens is this plus well, I mean, when the gate's closed, give me a second. I get a little confused here with these MOSFETs. The terminology is different. Drain to source and gate to source. Okay. Okay, your gate is like your base of an NPN transistor. Drain to source. Okay, yeah, and drain to source. Your drain is, you know, where the plus goes. You know, this is your drain right here, and your source is the ground. I guess source ground. So what happens is you apply to the gate. You apply a trigger voltage plus voltage 2 to 5 volts on the gate. And I guess it goes here to ground, and it closes the drain to source. And then your plus can channel through the coil through here. Let me make sure. Because 1 second. Okay. So give me a second here. I may verify stuff. Drain to source. Ah, there's a good one. That's a good guy. N-channel MOSFET. This is P-channel MOSFET. So channel 2 there, and then that there. Ah, it's the perfect image. Some diagrams are better than others. All right, this is a good diagram here. This music is kind of gothic. All right, here you have a nice diagram of a, I think it's an N-channel MOSFET. Right, N-channel MOSFET. Now this diagram explains how an N-channel MOSFET will stabilize the flyback. Okay. Clean up that image there. Oh shit. Excuse my language. Excuse me. Okay. All right. Here's where you apply your positive voltage. Here's where the coil connects. One end of the coil connects here, there. So your coil would connect here. Connect there. Can't show. And then it goes to the plus terminal of your source battery. Here's your minus. So let me do something here. Okay, so what happens here is you apply a trigger voltage of 5 volts or whatever, positive, to the gate, and you connect the source to the negative of your, to ground, which could be the negative of your trigger device, and that same negative connect to, to the negative of your source battery if you want, which is probably a good idea. So once you apply 5 volts and it channels through the gate out the source, that will cause the MOSFET to close the switch, and this switch will be closed, and then positive from your battery can flow through the coil to ground, to the negative of the battery, and charge up the coil. A 555 timer, or pulse width modulator, whatever you want to use to switch that gate on and off. And now, once you open up the gate and turn it off, this positive here that you put on the coil becomes a negative, and then the other side becomes a positive, and it flies back. That's the flyback. and it will go and damage this MOSFET. Okay, but because you have a, let me confirm this. Here, yeah. Pretty sure that's a diode, protection diode, one-way diode. So what happens is the positive goes, the flyback tries to cut through here. Can't go that way, but it can go this way. And you don't want it to, you know, to complete its path through the MOSFET to ground, because that will damage the MOSFET. So it tries to cancel the positive flyback by sending it this way, right here, and it'll keep going around and around and around until it stabilizes. Okay, because that diode eats up power, but the MOSFET itself is not capturing the flyback and conserving it in any way. I mean, it is conserving it in a way. It's, instead of letting the high voltage flyback hit the ground and damage the MOSFET, it lowers the voltage before it goes to ground by turning it around and around and around this path until it gets to a lower voltage, and then it'll go to ground. And that's why you use a control resistor or whatever, something like that. I think they use a resistor. So yeah, in a sense, a MOSFET will take the flyback and stabilize the flyback down to a lower voltage, and it'll bring the current up when doing that. So yeah, it does make efficiency out of the flyback, and helps you use the flyback in your load, because you know the load would be the coil. So it would go like this. Let me choose another color. Flyback in blue. Go around here. And meet up with the coil again. And if its voltage is still too high and it doesn't match the coil's voltage, it'll go around again. And each turn the voltage drops, but the current goes up. So I guess I wanted to explain it like this. The flyback voltage will go around this loop here, and it'll dump some current each turn into the load, into the source, which will enable the load to consume that current that it dumped each time. So basically, the high voltage flyback spike will go through this loop, dump a little current through the load. It'll help the load pass the current to ground. So the load will consume that little bit of current each turn. Then if there's still high voltage left, the second turn, it'll loop around again, and it will drop a little bit more current into the load path, which is down to the ground. And so by consuming the current in the flyback a little bit at a time, by dropping the voltage of it, it's being consumed through the load. as the load is being used. So yeah, MOSFETs are very efficient in that respect. They help you use the flyback in real time. So that's my my estimation of MOSFETs and how they handle the flyback. Society of High Sciences brought this up to me today, and I had to look into it. This is what I'm finding. On an N-channel MOSFET, your plus from the battery enters one end of the coil, out the other, and it's trying to get to ground over here. Has to go through the MOSFET to do that. So you would trigger the MOSFET to close the drain to source. And here's the drain to source path. So the first forward energy would go there, your normal voltage of, let's say, 12 volt battery. And then you open up the drain to source opens up and the flyback happens. And now you're talking, 300-400 volts with very little current, but that will still damage well, you have to keep these this flyback voltage below what the MOSFET can handle. So MOSFETs are designed to handle flyback, unlike your standard transistor. And it does like this. So the high voltage flyback, I'll do it in red this time. It will go through the drain to source gate channel, and some of that high voltage will get used through the load to ground. There will be more high voltage left over. It won't all get used because it has another channel to take for the high voltage to pass over to here, drop the voltage a little bit more while turning that into current and sending that current to ground and allowing the load to consume that current as it, because you got to understand that this energy is stored up in the coil. This flyback energy is stored up in this end of the coil. The current of that flyback and the high voltage is stored right here at that side of the coil. So, how do I do this? Where is the test? 1, 2. So each loop, loop that it does to get to ground, some of that energy is used. Okay? Let me do this another way. Okay, so the first loop used up some of the flyback. Now there's still the second loop here. Loops around to ground. And now you use up that portion of flyback. Okay, and some more voltage is dropped on that flyback. Now the third loop, voltage drops a little bit more, current turns into current and goes to ground. And it enables the coil to use that little bit of current in the flyback. And now it's used up again. And it keeps doing this until the flyback is stabilized. And the next loop up here of flyback energy goes through this channel, loops to ground, and enables the coil to use that amount of energy out of the flyback. And again, we got another little bit of more flyback energy left here. So loops again. and uses up that flyback until the last bit of flyback energy gets used up, like so. And now all the flyback energy is used up, and the voltage returns to the normal source voltage. So that's my approximation of how this is working. Okay, in red, flyback builds up right there, positive flyback, and it loops through one time, uses some of that current from the flyback. The next loop uses the next whatever's left in the flyback. The next loop uses that flyback. The next loop, and the next loop, and the next loop. And that's that. That's what I'm seeing here. So, in a sense, MOSFETs are good at maximizing efficiency by utilizing the flyback. If you have the load in series with the MOSFET to ground, and the load is a coil or a motor or whatever, a coil in the motor, the flyback generated on that DC pulsed coil, if it's using a MOSFET and you operate it, the MOSFET at its safe levels of voltage and all that, and flyback voltage, then it will efficiently use it all. So yeah, these are great inventions, these MOSFETs. From what I understand, an N-channel MOSFET can handle 1 amp, and a P-channel MOSFET can handle up to 3 amps. That's my presentation on MOSFETs and how they handle the flyback. To go over foolish engineers method, if you are running the MOSFET at beyond safe levels, you want to add stuff to protect the MOSFET, and he adds a flyback diode here. Now that's not going to store the flyback or conserve it in any way. It's actually going to cancel the flyback. How? Well, your plus flyback is on this side of the coil in green, and your minus flyback is here. So the plus goes through the diode and shorts out the minus. That's how you cancel the flyback. So that diode is just canceling the extra flyback that's left over to protect the MOSFET. So that's a great way to protect the MOSFET, but you will be losing energy from that flyback being canceled out. So that means the double pole circuit is still applicable for recycling the flyback away from the transistor. The MOSFET is a good one, but you're limited with MOSFETs on how much flyback, how high of a voltage you can generate of a flyback. So if you're using the flyback to experiment with vacuum energy, well, you want to go with a maximum flyback value of highest you can get it without burning out the transistor. And that's why Bedini was using those 2N3 3055s. They have a 100 volt breakdown voltage, and I'm pretty sure MOSFETs do not have that kind of breakdown limit. Bedini worked with MOSFETs. He was doing audio engineering work. He chose the 2N3055 because it has a high breakdown voltage, and he can turn up the amps more than he could do on a MOSFET without damaging it. And that way he can get a higher voltage flyback signal. Because the higher the voltage is, the more you tap into the vacuum, in my opinion. So it's not like Houdini was trying to sideline anybody or anything like that. He was just experimenting with vacuum energy. He wasn't experimenting with efficiency. He was trying to get beyond efficiency to a COP or more than one. MOSFETs will help you get to a COP of 1, but not over 1. So you have to experiment with high voltage spikes. Get them as high as you can get them. A standard relay that you buy will only go so far. You can build your own relay with thicker contacts, and that's a little bit of work. But the thicker the contact is, the higher the more amps you can send through it, and the larger the flyback signal will be. Oh, we got some comments here. Land Research, what's up, buddy? He clipped the flyback with neon bulb, have a small launch. Yes, right, the neon bulb. Which MOSFET are you using? N-channel MOSFET in the diagram here. What's going on how MOSFETs, Society of High Scientists brought it up to me that the MOSFET can handle the flyback. And yes, it can, but it can only handle a certain amount of flyback before it blows. So, and I'm saying that Houdini was trying to, increase the flyback voltage level higher, than what a MOSFET can do. But if you want an efficient system, definitely use MOSFETs. If you can lower your voltage input and switch it to lower voltage and keep that flyback to tolerable levels that the MOSFET can handle, then that will be a super efficient system. And yeah, but it won't be, a COP more than 1. And if you want to get that, you got to raise the voltage on that flyback big time. And there's no transistor that is on the public market anyway. It might be in the MIP market, military industrial, MIC, military industrial complex market, but it's not on our market. So, and I believe the only way to get a higher amperage and a higher voltage flyback signal, you really have to make your own relay. You can't even find a relay you can buy to do. Not that I know of anyway. So my idea for a relay looks like this. Yeah. That's what I would use. What you have here is a electromagnet. The field off the electromagnet is the field off the electromagnet is pushing the magnet on that arm away to disconnect the power, and then the magnet on that arm is pulling back to the iron core of that electromagnet when the electromagnet is off. So that's the basic concept of how to make a switch that can handle high amperage. Oh, by the way, those are gold-plated bus bars that a friend of mine gave me from high school. Gave me a box of them. Gold-plated bus bars. I'll probably end up using them once I get a nice design for a high frequency mechanical switch. So this is what you would call a mechanical switch. N-channel MOSFET. I heard that he found more flyback voltage when he placed the same circuit at a higher elevation from sea level. Yeah, that would make sense. The closer you get to the sky, the higher the positive potential is. And the closer you are to Earth, the more negative potential. I say that because the sun is protons. It's emitting hydrogen, and hydrogen's full of protons. I mean, it's more proton than it's one proton and one electron, I believe. Let me look at that. Let me check that out. And I just see protons and electrons as, you know, proton positive and electrons negative. That's why I say the sun is creating the positive potential. Yeah, so hydrogen is one electron and one proton. Most other molecules are like more electrons and still one proton, you know, or maybe two, I don't know, protons, but most other molecules have way more electrons than protons. But when you get to a hydrogen molecule, it's one proton, one electron. So in that respect, I say that the hydrogen molecule has proton energy to offer.
Charge it into the battery, and then you want to repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source.
So yeah, let's see here. Yeah, so when you put the device closer to higher elevation, you're getting closer to the sun, which is hydrogen, and it's donating. It just produces a proton exposure, and as well as an electron, but it's a balanced proton and electron. This, in my opinion, if you know, compared to other elements, they have more electrons and less protons. So, in my opinion, the sun is at a higher elevation, and that's what's creating the more positive proton potential. And of course, that positive potential is going to want to channel down to the negative, which would be Earth. And that's, yeah. You know, then again, they say lightning, you know, actually goes up first, then down. But, well, in knowing that, you know, the energy goes in two directions. Yeah, it's all hypothetical and, what's the word? Speculation at this point, but why would a circuit get more voltage at a higher elevation? Probably has something to do with the sun and its positive potential. The Earth is negative to the sun, and that's how the energy is being transferred. There are two different sources of energy, Earth and star. They have two different potentials. So yeah, well, I hope that that presentation was valuable to someone out there. Let's see here. So yeah, I was looking at this, you know, the the N channel MOSFET. So what I'm saying is the blue is your flyback buildup, and then in red is the flyback depositing on that end of the coil. and the MOSFET will recycle the flyback in a loop around the in that loop right there to ground, enabling the coil to consume the flyback a little bit at a time. Each loop it does, it diminishes the flyback potential in red dashes on the coil until it's all consumed, and then the flyback voltage stabilizes. That's my estimation on how an N-channel MOSFET will use up the flyback, the back spike. What you got? Bob Boyce. Why do I know that name? In Tesla conference, once said we have to use silicon carbide components or germanium when we play with scalar energy. Hmm. Silicon carbide. Well, what is silicon carbide? I mean, carbon, right? Components of germanium. I think a lot of this has to do with the carbon, the amount of carbon inside these elements, because this is a carbon planet, mostly carbon on this planet. So when scalar energy is planetary energy, If anybody wants to jump on and present something or talk about something, the link is in the chat here. We can talk about this scalar energy, anything you have to offer. I'd love to hear it. I am learning every day. Today I learned about this MOSFET, how it handles the flyback. I was in a live stream with Ben, and Society of High Scientists brought it up to me. And then it struck my curiosity. I was like, I got to figure out how this MOSFET is. I never really dived into MOSFETs. Let's see.
Come on. Do it. Do it.
Do it. Do it.
Well, I'm gonna cut this short. Getting late. I guess I'll play a video. Let it play through, and what's this one? Yeah, Lane Research. That's the thing about this flyback. You really do have to send it somewhere else. Um, you let the transistor trigger the induction to the coil. When the transistor opens, you have to be ready to move that flyback in another direction away from the transistor. And the genie found that way, he diverted it away from the transistor to the load, to the battery, to a battery, use the battery as a load. If you send it to a coil, that's not going to divert the flyback away from the transistor, because the coil will just, It'll capture the flyback and keep the high voltage on that coil for a period of time, unless you put a diode before you send it to the coil. And even a diode is not sometimes not enough, even the best diodes. But a battery with a high amp hour rating, which is why he said you got to have a certain amp. You got at least, he said, at least 7 amp hours on the battery. And he probably said that because the more capacity that battery has, the more ability it has to suck up the flyback and prevent it from leaving the battery back to your through your coil back to the transistor. So once you open up the transistor, it flies back through the diode, out the coil, through the diode into the battery. If there's not enough amp hours on that battery, it's going to go from the battery back to the coil and shoot through that diode, even though it's the wrong biasing, because it's such a high voltage. That's my opinion of why he said you got to have enough amp hours on that battery. And it's to efficiently suck up all the flyback, make sure it don't rebound back into your circuit. You could always test it out with a low amp hour battery to see, like a really small battery or something like, or just put like double A's in series till you get 12 volts. See what happens. You might see that neon light up even though it's going to the battery. It's a super high voltage. On the Bedini's coil, I remember getting 500 volts. I've made other coils with thinner gauge and more turns. One coil I made, I was reading 900 volts. My transistor never blew though, because I had that neon on there, and it never got hot either. So, and that still works. That build is still working today. It's in a box somewhere. It still works. The same transistor. Never had to change the transistor, but I had like I don't know how many. It was a lot of turns on that. It was 28 gauge, probably about 2 or 3 pounds of wire, and and that transistor never went bad, and I never went over 12 volts though. I'm sure if I hit it up to, I did for a short period. I did try 24 volts for a short run, but I didn't keep running it like that. And I believe it never went bad because the coil had so much impedance and so much mass, that any flyback that did come back from the battery back to the coil, the coil would get the rest and it wouldn't hit the transistor in a bad way. And that goes back to the mass of the coil and the amp hours of the battery and the mass of the battery. When you're dealing with high voltage, you need more mass to take that potential. That high potential needs to go into a higher mass. What's up, John? Yeah, you guys are like the silent vigilantes. You never join the streams or talk about stuff on the live, but I wish you guys would, the links in the chat if you guys want to discuss this topic on the radiant energy stuff. I'm getting 700 volts, 0.4 millimeter wire. What is that 0.4 millimeter? What gauge is that? Half a kilogram. That's like 1.5 pounds. I found the maximum power I get is 575 hertz, 90% boost. Yeah, every coil has a resonance point. Hmm. Yeah, I never tried to test out resonance on any of my coils with an oscilloscope, but that's what you would do. You would just pulse the coil and you see you get the highest peaks on the peak to peaks on your oscilloscope, and you know. I would just use the voltmeter to see how the receiving battery would respond. All right, guys, anybody want to join? If not, we'll go live again Sunday and maybe Friday. Ben's doing a thing on Friday. All right, I'm just gonna play a video and let it play. Okay, John, let me make you a mod. Hold on. Are you a mod? Yeah, post the link. You're a moderator, so you can put the link in the chat there, and I'll play it. Post the link.
Do it. Do it.
Do it. Do it. Do it. Do it.
Do it.
Who is doing it? Do it.
I have learned how to make homemade flow batteries that use just the cheapest ingredients you can imagine. With the same chemistry, we can create acids that dissolve metal ores out of rock, and then just as easily deposit the metal again in a pure form. We can generate and pressurize hydrogen in a single step, and produce all manner of expensive chemicals from nothing but a solar panel and salt. All of this uses the same core technology and can be done using items purchased from a local hardware store. My goal is for this video to be the best introduction to the incredible, practical applications of electrochemistry that you will ever watch. Hi, I'm Ben. Thank you for being here. Electrolysis is the basis of every project we will put together in this video, a word which literally means to break stuff with electricity. The basic experiment that most people will have seen on this topic is when electricity is passed through water. It splits into oxygen and hydrogen gas. Oxygen bubbling up from the positively charged electrode called the anode, and hydrogen forming on the negative electrode called the cathode. This confused me very much when I was a kid. Have you ever thought about how this works? If this is truly just a reaction where water, H2O, cleanly splits in half when you add electricity, how is hydrogen ending up way over here on the cathode and oxygen over here on the anode? Does a water molecule split in the middle of the tank and just shoot off the individual gases at lightning speed toward whichever electrode they're attracted to before they can bubble to the surface? That does not make a lot of sense to me, but it's the best explanation I could imagine with the information that I had. H2O plus electricity equals oxygen and hydrogen. I want to show you something that will reveal that this experiment is a little more complicated than the explanation you might have learned in a middle school science class. And I promise, this information is relevant for making our homemade flow batteries and all the other technology mentioned earlier. This will pay off. So I have a shallow container of fresh water here with my 2 electrodes sticking into it. I have added a pinch of sodium sulfate to this water to make it conductive, but ignore that for now. We'll talk about how salts interact later. To this water, I'm going to add a liquid pH indicator. This is a liquid that turns green when it's at neutral pH, and it changes to red in acid, and blue when it becomes alkaline. Now I'll turn on the electricity and watch what happens. Interesting, isn't it? We are generating acid at the anode and base or alkaline conditions at the cathode. This is obviously not a simple one-step reaction where H2O just cleanly splits in half. There are 2 different chemical reactions going on here, at least. One of them is making acid and the other is making how to make homemade flow batteries that use just the cheapest ingredients. Over here on the flow batteries, when it becomes water electrolysis, obviously not a simple. Interesting, isn't it? We are generating acid at the anode and base or alkaline conditions at the cathode. This is obviously not a simple one-step reaction where H2O just cleanly splits in half. There are 2 different chemical reactions going on here, at least. One of them is making acid and the other is making base, in addition to the gases that are produced. And in fact, this is the key to understanding how water electrolysis really works. It consists of multiple reactions that are occurring simultaneously. At the cathode, the addition of electricity, or technically just an electron, to H2O kicks off one of the hydrogen atoms as gas, leaving the other hydrogen behind stuck to one oxygen. This is an OH ion, which remains in the water. If you look up some of the most caustic alkaline chemicals in existence, you'll see that this OH ion is the thing that makes them so very basic. For example, this is lye, this is ammonia, and this is lime, all of them very strongly alkaline. So this side of the solution accumulates these alkaline OH ions and turns blue. At the other side, the positive electrode rips electrons off of water molecules that are nearby. Now, the reason that hydrogen and oxygen like to stick together in the first place is that oxygen is the most stable if it has 2 more electrons stuck to it, and hydrogen atoms have 1 electron each. If those electrons are ripped away by the pull of electricity through a power supply, well then the hydrogen loses the one thing that made it stick to oxygen to begin with, and the water molecule just falls apart. Oxygen bubbles away as gas, but the hydrogen is now in a very unhappy state. It is so unstable without its usual electron that it immediately sticks to anything that it can. In this case, just a nearby water molecule, so it never bubbles away. This forms H3O, a hydronium ion, which is maximally acidic. So that side of the solution turns red. But if you mix both sides of the chamber together, you can see that the acid and base fully cancels out, leaving the solution its original neutral green. The end result is that H2O plus electricity does equal oxygen and hydrogen gas. That's not a completely inaccurate summary if you ignore the side reactions that cancel out. But for me, knowing that electrolysis causes these completely different reactions at each electrode, well, that explains why oxygen and hydrogen bubble out separately. They didn't originate from the same molecule of water being split in half. Now, this pair of distinct reactions at each electrode is where the magic is that allows flow batteries, metal refining, and a whole host of different chemical processes to be possible. Let's consider metal refining, which is just an awesome application of this technology. When you have some metal ore, say a rock that is high in iron, like this magnetite, which is iron oxide, you need to strip off the oxide part to leave the iron behind in a metallic state. This can be done by mixing it with coal and firing at extremely high temperatures so the coal binds to the oxygen part of iron oxide and floats away as CO2, leaving iron to come out of the furnace as relatively pure metal. Or we could use electrolysis, the first step of which is to dissolve the rock in acid. And that, we've already seen, can be supplied by the positive electrode of an electrolysis device. So this is a very simple electromining setup designed to produce acid on this side of the cell, use that acid to dissolve metal ore, and then also process the dissolved metal into a purified solid state. There are a few aspects of this cell that we have not yet explored. This barrier that surrounds the positive electrode and the central barrier which separates the two sides. These prevent the liquid in each compartment from mixing with the others, so the chemistry that occurs at each electrode no longer cancels out in the middle. These barriers do not conduct electricity, which is very important, or they would just act like a third electrode in the middle of the tank. Instead, this material only allows dissolved atoms or molecules that are carrying the correct electric charge to pass through, while blocking everything else. These are called ion exchange membranes, and I will be showing you how to make them. Examples of ions that can travel through these membranes are the alkaline OH groups that are generated at the negative electrode, which have a strong negative charge, and the acidic, positively charged hydrogens which form on the opposite side. Actually, everything that dissolves in water splits into ions when it does so. For example, table salt splits into a positive sodium ion and a negative chlorine one. This central membrane only allows negatively charged ions to move through it, so chlorine gets a pass, but sodium would be blocked. The opposite is true for this membrane, which allows positive ions, like acidic hydronium through, but denies OH or chlorine, which is precisely why it's there. The first thing that this cell needs to accomplish is to generate an acid that can dissolve my ore, and hydrochloric acid is the option that works best. If I dissolve table salt on this side of the cell, the chlorine in the salt should react with the acidic hydrogens that are generated at the positive terminal to form hydrochloric acid. But there's a problem. In pure water, the reactions at each electrode take place exactly as we've discussed previously. But when you start involving extra chemicals like table salt, sometimes those chemicals are the ones that more easily participate in the reactions at the electrodes than water itself. If a negatively charged chlorine ion steps in at that positive electrode and has an electron ripped off of it, it stops being negatively charged, which is the thing that made it an ion to begin with, capable of being dissolved in water. Instead of making acid, that difference in one electron transforms harmless dissolved table salt into chlorine gas, which is not the thing that I'm looking to make. So this second barrier has the one and only job of keeping chlorine ions away from the positive electrode. In this little compartment, I put a pinch of sodium sulfate and fill it with water. There's no chlorine in sodium sulfate and therefore no risk of chlorine gas. The rest of the chamber on both sides of that central membrane gets filled with a dissolved solution of table salt. I'll add a few drops of pH indicator just so we can more easily see what happens, and then turn on the power. Fairly quickly, we start seeing acid form on the positive side, as acidic hydrogen ions are produced in the tiny compartment and, being positively charged, are allowed to pass through the positive ion membrane. These react with the chlorine in table salt in our secondary compartment to form our desired product, hydrochloric acid. In fact, any salt that we dissolved in this compartment will form its respective acid. Sulfates make sulfuric acid, nitrates produce nitric, and so on. Now, on the other side, as alkaline OH groups are produced, these join with the sodium part of table salt to form sodium hydroxide Li. For this iron refining setup, we actually want both sides of the cell to be acidic because alkalinity causes dissolved iron to fall out of solution as iron hydroxide, and we don't want that. So these alkaline OH groups need to go. To fix this, we just let the cell run for a while until acid and base build up, and then we empty the alkaline side, refilling it with fresh salt water. This removes alkalinity from the system while leaving the acid untouched, so acid continues to build, and after doing this 2 or 3 times, we have an excess of very strong acid in the positive compartment and very little alkalinity left to fight it. The final step is to just transfer a few drops of acid across the membrane to make both sides of the cell acidic and ready to refine some metal. In case the wonder of what we just did was lost on you, we just made hydrochloric acid from table salt and water. Now we get to use this acid to dissolve rock. My magnetite sample is crushed into a fine powder and placed into a second dish where acid from the electrolysis cell is piped over. After a few hours, the rock will be mostly dissolved, and the iron-rich liquid is now transferred back into the cell, this time on the opposite side. This solution contains the result of hydrochloric acid's reaction with magnetite, which is iron chloride. Now remember what I said about adding new chemicals to an electrolysis cell, that sometimes those chemicals will be the ones that react instead of water. And that is exactly what happens with iron chloride at the negative electrode. Instead of water receiving extra electrons and giving us hydrogen gas, the iron chloride receives an electron, releasing negatively charged chlorine ions into the water, and metallic iron plates onto the electrode. And here's the best part. At the same time as pure iron is being extracted, the chlorine ions that are released in the process are able to cross back through that central membrane into the other chamber, where they are regenerated into more hydrochloric acid. This is a closed-loop system. The only thing that needs to be added after the initial input of water and table salt is electricity and fresh ore to be refined. Just look at this beautiful sample of pure iron that I plated out earlier. Now, there is some nuance in making this setup work optimally, and those who already know something about electrochemistry will have some questions, and I'll put more detail about how this process works on screen now. What I'd like to point out is just how many things we were able to do with this one little cell. We started with water and table salt and made hydrochloric acid, sodium hydroxide, oxygen gas. We refined magnetite into pure metallic iron and made a little extra hydrogen gas on the side. That is a lot of stuff to get done, and I'm only running this cell at 1/3 of a watt of electricity. Just imagine what you could do with a system scaled up to use the power from a 200-watt solar panel. By the way, now that this has run for some time, if I disconnect the leads of the power supply and instead poke at these electrodes with a multimeter, this cell is now actually producing some voltage. On top of everything else, this simple, incredible metal refining setup is also a battery. I've been using Delete Me, my sponsor for this video, for nearly 3 years now. Since then, hundreds of data brokers that in the video become plans by using my right now. I'll put right now. I'm using the code Nighthawk on checkout. I'm holding myself back from continuing to talk about flow batteries and all the other applications we could dive into right now. I'll put that off until later in the video because I think it's time that we learn how to actually make the key to all these technologies: ion exchange membranes. Commercial varieties of these cost hundreds, even thousands of dollars per square foot. These ones cost maybe $1 and can be easily made from common hardware store items. Because these are so accessible, before I show you how to make them, let me give a brief word of caution. Obviously, what we've just seen is that electrolysis can make very strong chemicals that will cause severe injuries if mishandled. It can also produce many toxic chemicals like chlorine gas, lead and chromium salts that will contaminate the liquid if you use the wrong electrode material, or if you dissolve metal ore that contains anything toxic, which is almost guaranteed to be the case. So doing anything with electrolysis that is beyond your understanding is very likely to make unintended toxic waste that you are not equipped to handle or dispose of. Be cautious. Learn everything you can about an experiment before trying it, and ideally, find real human beings that have chemistry experience to help you do things safely. The person responsible for this particular membrane recipe is Robert from the YouTube channel Rowow. On that channel, Robert has been developing professional electromining equipment using these membranes in the hope of seeing them change the mining industry, as even the tailings that are discarded by conventional mining could be easily extracted for all the valuable materials they contain. Simultaneously, the warning that I gave in the safety disclaimer about extracting toxic things becomes an advantage if it's being done intentionally. The mining waste is depleted of toxicity, so it's safe to return to the environment, and in the right context, that toxic material, like lead and cadmium, becomes a valuable resource. The membranes that make this possible are based on this paper published in the year 2000. Robert spent 2 years learning how to replicate the results of this paper using simplified materials and methods, and as of this year, has published that improved process under the public domain, so everyone is free to benefit. These membranes are made using off-the-shelf PVC cement and resin beads, which are a common component of water softeners. These beads can be easily purchased or even removed and recycled from an old water softener that is being replaced. The two basic types of resin which most membrane electrolysis projects call for are cation resin exchange beads and anion resin exchange beads. Cation beads make a membrane that allows positively charged ions to move through, and anion beads do the opposite, allowing negative ions to pass and blocking everything else. The membranes are as easy to make as grinding the resin of choice into a powder, mixing it 50-50 with PVC cement by volume, and spreading this liquid onto a silicone or polyethylene sheet to dry. That's it. This variation is super easy to make, but the membrane does come out a little bit fragile, so an upgrade is to paint the liquid onto woven fiberglass. The fiberglass greatly increases the strength. To go a little more in depth on this process, there are a few important details for success. Grinding the resin beads can be difficult, and a large part of Robert's efforts went into finding an appropriate method. This is the style of grinder to use, a high-speed spice grinder. You can pick one of these up on Amazon or eBay, and I'll have some affiliate links in the description below. A word of caution, these are a dangerous tool. There is no safety on this grinder to prevent you from bumping the on switch while the top is off, and it's as powerful as a lawnmower. I always unplug mine from the wall before opening the lid. It is not a toy. With this grinder, the cation resin is easy to process and basically just involves filling the grinder halfway and letting it run for 5 minutes. You don't want to let these resins ever dry out or they will lose functionality. So it's best to keep them in an airtight container with a little bit of water at the bottom. If the resin is too wet, it will stick to the sides of the grinder and you'll have to tap it with a mallet to get it to fall into the blades. Anion resin can be prepared in almost the same way, but it's stickier and will not grind properly unless you add about 2 teaspoons of talc powder for each half cup of resin in the blender before turning it on. This lowers the stickiness and allows the anion resin to reach a fine powder without clumping too badly. Both resins, once fully powderized, should be sealed in airtight jars, so once again, they don't dry out. The cation resin easily mixes with PVC cement just as described. Just mix it 50-50 by volume and stir it together. But the anion again requires just a little more care. For each heaping teaspoon of anion resin, I find that it helps to add 3 milliliters of PVC primer to turn the resin into a paste before adding the cement. Otherwise, the resin is a little too thick and it's really hard to mix into the cement without forming clumps. Premixing with primer solves this issue, and it also colors your anion membranes purple so you can remember which is which. The membranes should all be stored in a plastic bag with a spritz of water inside. So with the membranes in hand, let's get back to battery technology. We've already seen one method that can be used to make a surprisingly effective battery. The little iron refining cell is in no way optimized for power storage, and yet it delivers a very respectable 1.6 volts and 35 or 40 milliamps. It does this because the iron plating chemical reaction is reversible. You put electricity in to extract the iron, and you get electricity back if you let it dissolve again. If we want more power, the only thing that needs to be done is to bring the electrodes closer together and make everything bigger. So let's make a big one with a few modifications to optimize for a battery instead of metal extraction. To make things simpler, I'll avoid using any chlorine in the cell, so we don't need that extra little compartment to surround the positive electrode. And in fact, we can use just a single cation membrane in the center of the cell, which is the type that only allows positive ions through it, and it's the easiest kind to make. So I've cut out a little piece of membrane here, and we have a few options to hold this in place inside of our plastic container. The best, if this container were also made of PVC, would be to use PVC cement, since that is exactly what the membrane itself is made of, and it's very chemically resistant. Second place would maybe be RTV silicone. And then third, in terms of chemical resistance, but first in terms of practicality, is hot glue. Hot glue actually stands up surprisingly well here, and it's definitely the easiest to quickly glue a membrane in place. It technically does start to break down in very high and low pH, but in practice, it takes many months before needing to be repaired. It may never break down in this case because the battery chemistry we'll be using is quite mild. A long-term solution for harsher conditions would be to hold the membrane in with hot glue and then smear RTV silicone over top of it as a protective layer. For this project, I bought a hot glue gun that has this extended nozzle on it to make reaching into tight spaces much easier. If you want one of these, again, I'll have affiliate links in the description. To make sure you get a strong connection with the plastic surface, just make sure that the hot glue is very hot when you apply it, and you'll be sure to have a secure and waterproof connection with the membrane. Bonus tip: if you ever want to remove hot glue, just apply a little rubbing alcohol, and in a few minutes it'll peel right off, even from a rough and textured surface. Well, we have a bigger cell. Now we just need bigger electrodes. For both electrolysis and battery tech, the more surface area that the electrodes have, the more amperage or current a battery will be able to deliver. The best off-the-shelf electrode option for most DIY projects is graphite. It's non-toxic, it's conductive, and it doesn't easily react with harsh chemicals. Graphite rods can be purchased for welding purposes, sold under the name of gouging carbons. Most of these will be coated in copper, which can be removed chemically or physically with sandpaper, but both of those options are a messy process. So it's better to buy uncoated carbons to begin with, if you can find them. Another option is graphite foil, which you're less likely to find in a hardware store, but it's very easy to find online. This stuff can be cut with scissors into any shape that you'd like, and it makes an excellent electrode. Not, however, as good as this. This is conductive carbon felt, which is the gold standard for battery electrodes because it has an enormous surface area for its size. But I didn't purchase this as is. Conductive carbon felt is way too expensive, so I was forced to figure out how to make my own. And this, it turns out, is better than the stuff you can buy anyway. To make this, I start with carbon felt that is sold as fireproof welding blankets. And this stuff is cheap, about $25 for a 4-pack of giant sheets. Now, I wish this would work as electrodes right out of the box, but sadly, this felt is not conductive at all. To make it conductive requires 2 steps. First, we blast it with a torch or throw it into a fire to burn off all of the disgusting volatiles that are left over from however they make this stuff. Do not breathe this smoke. It is certainly unhealthy. Using an open flame really helps keep this process clean because most of the volatiles fully burn away instead of being released as noxious smoke. Once the felt has been thoroughly cooked, it should be handled with gloves and breathing protection because it's kind of like fiberglass. It will get irritating little needles into your skin, and you of course would not want to inhale any of that as dust. At this point, it's still not conductive and requires a final step of cooking it to about 3 or 4 times hotter than a torch could hope to achieve. And this is done in a microwave. I made this microwave kiln specifically for cooking carbon felt electrodes. This is ceramic fiber blanket, which is surprisingly cheap. This roll cost about $15 and is rated for 2,700 degrees Fahrenheit. I rolled this up with a big enough cavity on the inside to slip in my carbon felt and tied it together just with a bit of twine and used a few scraps to plug the ends closed. This goes into a microwave. Outdoors. Good gracious, do not do this inside your house. And I turn it on for 8 to 10 minutes. The carbon felt becomes absolutely white hot in that time, and then before it fully cools off, I pull it out and submerge it in water. This does 2 things. It cools the carbon down before it reacts too much with the air, and it also stops the felt from throwing off those fiberglass-like needles as dust. Once it's made, I always keep this wet so that dust is no longer an issue. And this is the best electrode material you are ever likely to see. It has extremely low electrical resistance, extremely high surface area, and is very resistant to the strongest chemical solutions. With this for our electrodes, let's turn back to our battery project. This is what I came up with as an electrode design for my bucket battery here. I have a piece of scrap wood with some holes drilled through it that fit my carbon welding rods. And these stick down far enough to dip into the bucket on either side of the membrane with attached strips of carbon felt. Opposite to the carbon rods on each side is a fiberglass rod cut from a reflective driveway marker. To attach the felt between the graphite and fiberglass on each side of the plank, I use zip ties. And for extreme chemical resistance, you could also sew them on with PTFE dental floss. So I place this assembly into the bucket, and now we just need to fill it up with an electrolyte solution. For a chlorine-free, iron-based battery, the best option as an electrolyte is iron sulfate. This is a common fertilizer and also a waste product of iron manufacturing. It is extremely cheap in bulk. We can dissolve about 200 grams of this in 1 liter of water, and then add about a teaspoon or 10 grams of citric acid, which can be purchased in the canning section of most grocery stores. Citric acid is a stabilizer that prevents the iron sulfate from turning into rust or other insoluble compounds when the battery is cycled. Once dissolved, this liquid can be added to the battery, and that's all there is to it. Let's hook it up to a power supply and give this a charge at about 1.6 volts. After about 12 hours, the battery starts drawing less current, which indicates that it's charged. In an iron battery, you can also tell the state of charge just by looking at the color of the electrolyte. The positive side will be much darker than the other. This time we're not plating iron off as solid metal. The citric acid added to this solution prevents that from happening. Instead, we're splitting the iron sulfate into two different iron compounds, both of which remain fully dissolved. This is again a reversible chemical reaction, where the two iron compounds want to be balanced on both sides of the membrane, but the input of electricity has forced them into a very unbalanced situation. Undoing this imbalance generates electricity because ions have to move through that central membrane to restore equilibrium, taking a positive electric charge with them. And you can't just move an electric charge like that without completing a circuit. So, if we attach a wire between our two electrodes, when the ions move, they have to force electricity through this wire to balance the charge that their movement creates. And look at that. We have electricity. That is awesome. Using our multimeter, this battery gives us a reading of about 1/4 amp at 1.2 volts. Increasing the amount of iron sulfate in the electrolyte to 300 grams per liter will double the amperage, as long as you keep the battery warm enough for the extra iron to stay in solution, about 70 degrees Fahrenheit. You can push the amperage even further by adding sulfuric acid to the cell, which greatly increases electrolyte conductivity. But doing so, of course, requires more safety in how these batteries are designed and stored. This is a single cell, meaning there's only one membrane dividing two electrodes. Commercial batteries use multiple cells chained together to reach a higher voltage. If I connect this in series with another identical cell, we should end up with twice the voltage. Now, this should be able to make our little motor here spin significantly faster. 10 of these cells would make a 12-volt battery. Not quite equivalent to a car battery, because the amperage is much lower. But these cells have one significant advantage. The total amount of power that they can store is basically unlimited, because this is a flow battery. In a standard chemical battery, at least one of the reactions involves chemicals that plate onto the electrodes in a solid form, like metallic lithium or iron or lead. And that means if you want to store more power, you have to increase the size of the entire battery to make room for more solid material near the electrodes. But in a flow battery like this, the charge-carrying ingredients are all completely liquid, which means you can store more power by simply adding larger liquid storage tanks. The size of the actual battery, meaning this part here with the electrodes and the membrane, can stay exactly the same size. Just connect this up with a few aquarium pumps to some pickle barrels full of more iron solution to pump through the cell during charge and discharge, and suddenly this little bucket battery will have multiple kilowatt hours of capacity. Now, it can only give that back to you at a few volts and half an amp, but it can do that for a very, very long time. Increasing those volts and amps is where scaling up the actual electrode area, and especially the cell count, is still probably necessary. Thankfully, there is an easier way than just stacking more of these buckets next to one another, and that is to put multiple cells in the same bucket using dividers. Something like this little container is a great way to get about 4.8 volts out of 4 divided cells wired in series. And to deliver more amps, we could increase the size of this design to something like a plastic storage bin. Now, I'm not going to go into detail of how to set up the plumbing for the external tanks of a flow battery in this video. So if you want to see more on that topic, let me know. Maybe I'll continue building on this flow battery project in the future. Now, hydrogen production is another project that this membrane technology offers a massive upgrade to. Years ago, I made a video about water electrolysis and made several designs that offer various benefits and downsides. The biggest challenge to solve is how to produce a lot of hydrogen efficiently without allowing it to mix with the oxygen that is produced at the positive electrode. The closer the electrodes are to each other, the more efficient the gas production, but also the more difficult it is to keep that oxygen and hydrogen separated. If the gases are allowed to mix, the result can be extremely dangerous, as even a tiny bubble of this perfectly balanced oxygen and hydrogen mixture is enough to make your ears ring. My solution years ago was to place the electrodes in separate plastic hoods, far away from each other, so that when the bubbles form under the hoods, they float up and out of the container without mixing. But because the electrodes were not only far apart, but also the path between them was blocked by plastic, this required a lot of power to generate the gas. An ion-permeable membrane changes things significantly. By separating the two electrodes with this, we can stop the gas from mixing without blocking the flow of conductive ions. This way, the electrodes can almost be touching one another as far as the power is concerned, but the gas is divided. There are multiple ways we could build a cell with this concept, but this is what I've put together for now. This uses an anion exchange membrane, hot glued into a cylinder with an electrode extending into the center from above. Onto the carbon welding electrode, I've zip-tied a strip of carbon felt, which uncoils inside the membrane chamber so it presses as close as possible against the outside wall. The threaded pipe which attaches to the membrane assembly has a gas outlet on the side to collect the hydrogen as we produce it, and a threaded cap tops the whole thing off with a hole made for the carbon rod to poke through, sealed in with hot glue. The external electrode which connects to the positive lead from the power supply this time is not made from carbon felt. I'll be using a solution of sodium hydroxide as my electrolyte, which is one of the rare things that's pretty tough on carbon when you pass a positive current through it. The carbon felt would dissolve fairly rapidly as the oxygen made in this process facilitates the hydroxide in converting the carbon into carbonates and other organic gunk that can clog up the membrane. This is not a problem at all for the negative electrode, but for the positive one, I'll be using a nickel sheet, which is more inert in these particular circumstances. Nickel sheet metal is easy to buy online because it's commonly used for electroplating. To use this hydrogen generator, I dissolve as much sodium hydroxide as possible in a container full of water, being careful with eye protection and gloves because this stuff is very corrosive. And then I take some of this solution and fill the inner compartment of the electrolyzer. The whole thing then gets submerged in the container, and I can connect up the leads of my power supply. This is now generating hydrogen gas, which can be collected from the end of this tube. What we're looking for to determine the efficiency of this setup is for the amperage delivered by the power supply to be as high as possible, with the voltage set as low as possible. At 4 volts, that is a lot of amps for such a small setup, and you can see that the gas is flowing fairly nicely. One way to tell that this is pure hydrogen is if you make a bubble and knock it free of the tube, it should float to the ceiling. It's a little easier said than done. Let's see if I can do it. Try again. There we go. Maybe the biggest advantage of all that this type of hydrogen cell offers is that the gas output is automatically pressurized as it's generated. The membrane causes the central chamber to be fully sealed, so however much pressure that membrane can take before bursting is the pressure that can be provided at the gas outlet. This is the first cell I've made that can fill a balloon straight from the outlet with no compressor in between. Now, I only trust my hot-glued membrane cylinder to stand up to a few psi at most, but with the right structural support, this type of generator can theoretically achieve almost 3,000 psi without a compressor, straight from the hydrogen outlet. That could be quite useful, to say the least. Well, I think that probably was enough to pique your interest in membrane electrolysis. Check out Robert's channel ROAL and thank him for sharing his membrane formulations. If you're interested in more information about using this technology, especially for mining purposes, he has an excellent library of videos, including this one, which is a great high-level overview of the core principles of the closed-loop system he's working on. There's also a very casual interview posted on my second channel where Robert and I talk about all manner of electrolysis topics. Well, if you followed my recent community posts, you might have seen that I was not in great health through this past winter. And thank you to everyone who continued watching these videos and supporting me, especially through Patreon in the meantime. I think I'm much better now. In any case, I'm feeling great at the moment. And that's something to be thankful for. This was a monster of a video to research, and I had to learn about electrochemistry at a much deeper level than I expected. Several unmentioned experiments that I worked on for this video turned out to be dead ends, because somewhere I started with an incorrect understanding that required weeks of intensive research to unravel. I hope that paid off somewhat in being able to better communicate these pretty difficult chemistry topics in a way that's digestible and inspiring to make you want to learn more. If I pulled that off and you found this video valuable, you can support my future efforts, again, on Patreon. If you can't afford it, no worries. Please don't send me money if you're having a hard time yourself. Only if you have extra and you like what I'm doing here. I'd appreciate it. Thank you so much for watching. Leave me comments below. It's been too long since I've posted a video and I miss hearing from you all. Thanks for watching. I'll see you next time.
Come on. Do it. Do it.
Do it. Do it. Do it. Do it.
Do it.
Who is doing it? Do it. Do it.
All of it.
Do it.
Come on. Do it now.
And I will do the rest.